Hello, this is the third video of the second order differential equation series 2 on non-homogeneous equations for OCR Pure Core Further Mathematics. And this video looks at finding particular integrals for polynomial functions. In general, to solve an equation of the form a d2y by dx squared plus b dy by dx plus cy equals some function of x, first we find the solution to the corresponding homogeneous equation, where you will remember that instead of equaling f of x, we would set that equation equal to 0. And this solution is called the complementary function. We then need to add a function to give the correct right-hand side, known as the particular integral, and we may do this by trial of a similar function to f of x, giving the general solution y equals the complementary function plus the particular integral. So here is an example. To find the general solution of the differential equation given below, first we would solve d2y by dx squared minus dy by dx minus 2y equal to 0. In other words, the homogeneous version. This gives us an auxiliary equation which we have met in previous videos, resulting in m equal 2 or m equals minus 1, and therefore a complementary function y equals ae to the 2x plus be to the minus x. So we have the complementary function, and now we need to try and find the particular integral. Let's try the same form as f of x, in other words a quadratic. So, setting y equal to ax squared plus bx plus c, that would, on differentiating, give us dy by dx equal to 2ax plus b, and d2y by dx squared equal to 2a. If we then substitute these ax squared plus bx plus c, the 2ax plus b and the 2a into, we can see that we would get this expression here, and that will then equal the f of x from the original differential equation. Let us then compare the coefficients to work out the values of a, b and c. So for x squared, we know that we're going to have a minus 2a must equal 3, giving us a value of a equal to minus 1.5. For the x coefficients, we will have minus 2a minus 2b must be equal to 7. And this results in a b value of minus 2. And for the units, we would have 2a minus b minus 2c equal to 1. Using the values of a, this would give us minus 3, and for b, plus 2 minus 2c equals 1, and therefore c equals minus 1. So therefore we can use these values for a, b and c in the particular integral. Thus leading us to the general solution, where we have that y equals the complementary function, and then plus this particular integral with the values of a, b and c as identified in the previous slides. So let's have a look at the solution curves. You can see here that the blue dotted lines show e to the 2x and e to the minus x. And here we have a equals 1 and b equals 1. Let's see what happens as we adjust these values. Here we can see there is a local maximum for small x. because of a relative strength of a complementary function and a particular integral. When a and b are set to 0, then you have a purely negative polynomial or negative quadratic curve. And then as a and b increase in value, the complementary function overpowers the effect of a particular integral on the curve. You may note that at the point x equals 0, y will equal a plus b minus 1. In looking for particular integral trial functions, we have now seen that if f of x is a linear function, we will use a trial function of ax plus b, and for a polynomial function of order n, we will use a similar order trial function. In the next video, we will look at particular integrals for trigonometric functions.